Good day everyone, and welcome to week 8 of the ordinary differential equations class. And so in this week we are going to learn a little bit of theory of higher order linear differential equations, and we are also going to learn a little bit about Laplace transform. Well, I have to admit that this is my least favorite topic in the whole course, and the reason is because the theory of higher order linear differential equations follows from the theory of systems of differential equations in a trivial way. And Laplace transform, although it is a very highly applicable topic and very, very useful in engineering, for example, but in my opinion, it is not very much related to the theory of differential equations. So rather, I think it belongs to complex analysis. But anyway, let's see what this is about. So here is a higher order linear differential equation. And an initial condition for a higher order linear differential equation specifies the value of the unknown function, the value of its first derivative, second derivative, and so on, up to derivative of order n-1. So for example, I don't know, so let me write down some example. So suppose that I have derivative of order 4, right? So plus, say, cosine t times second derivative, right? So plus ln t times y equals some function, I don't know, e to the minus t, whatever. And so since logarithm is present, it means that t has to be positive. So let me specify an initial condition, let's say at the point, I don't know, 3.5. And so y 3.5 is 0, y prime at 3.5 is minus 1, y double prime at 3.5 is, say, 2.7, and finally the third derivative, y triple prime at 3.5 is, I don't know, 0.6, whatever. So this is a well-posed initial value problem for this fourth order differential equation, right? Since the differential equation has order 4, it means that we need to specify the value of the function, its first derivative, second derivative, and the third derivative, so up to order n-1. And again, we have the theorem of existence and uniqueness of solutions, just like we have it for first order and second order differential equations. Then if our equation is linear, then suppose that we know that our function, our coefficients are continuous on some interval from alpha to beta, then for a linear differential equation, the solution exists and is unique on the same interval. And so for a nonlinear differential equation, existence and uniqueness still hold, but the domain of the solution may be smaller. So just like for first order differential equation. So the only thing that is really different now is that the initial condition has specified the values of the function and its first derivative and so on, all the derivatives up to order n-1. Well, so then for a linear differential equation, if its right hand side is 0, then the equation is called homogeneous. Then the set of all solutions of a homogeneous differential equation is going to be a vector space of dimension n, and the theorem of existence and uniqueness of solutions gives us an isomorphism with Rn. A good problem to test your intuition is what is the Wronskian of more than two functions. And so I suggest that you pause the lecture and try to guess the answer, and then Alright, so and the answer is, of course, suppose that we want to, let me do the Wronskian of three functions first. So the Wronskian of, say, f, g, and h. It has to be some kind of determinant, and the three functions must be involved. So we need to write f, g, h. But then we have to involve the derivatives, f, g prime, h prime. But then now we only have two rows and three columns, so we need to write one more column, and of course we are going to write f double prime, g double prime, h double prime. So that's the Wronskian of three functions. So the Wronskian of, I don't know, n functions are going to be f1 and so on up to, say, fn. It's going to be the determinant, where the first row is the unknown functions, the known functions are the given functions f1, f2, and so on, fn. The second row is the derivatives, f1 prime, f2 prime, and so on up to fn prime. And the third row is going to be the second derivatives, and so on. And row n is going to be derivatives of order n minus 1. The first function, and so on, up to the derivative of the order n minus 1 of the nth function. That's the answer. And all the theorems about the Wronskian, they are pretty much true for high order differential equations. So there is Abel's formula that the Wronskian is going to be e to the power minus antiderivative of the coefficient at y prime, I think, as far as I remember. Yeah, well, anyway, you can check the textbook. The important feature of the Wronskian is that if our functions are solutions of a high-order linear differential equation, then the Wronskian detects whether they are linearly dependent or independent. So either the Wronskian is 0 on the whole interval, and then the functions are linearly dependent, or the Wronskian is positive or negative, so it is never 0 on the given interval, and then the functions are linearly independent. So, and this only applies to the case when our functions are solutions of the same differential equation. And of course, just pretty much like for second order differential equations, if our differential equation is not homogeneous, if there is a right hand side present, then the set of all solutions of this can be described as some particular solution plus the general solution